good morning, good afternoon, good evening, good wherever you are, and welcome to another SNEAR presentation from the Cloud Storage Technologies Initiative. Today we're going to be talking about high-performance storage at Exascale, which is a scale bigger than anything I've ever encountered before. This webcast is going to be brought to you by the following experts in their field. The first I'd like to introduce is Dr. Torben Kling-Petersen. Hello, Torben, how are you?
I'm good, thank you.
Excellent. Torben is Principal Engineer at HP Storage BU in HPE. We're also joined by Michael Henneke. Michael, how are you?
I'm great, thanks.
Good. And Michael is Principal Engineer of HPC Storage at Intel. And last but not least, my good friend Glenn Bowden. How are you, Glenn?
Yeah, good, thanks, Alex. Good to be here.
Good, good. Who's Chief Architect, AI and Data Science Practice at HPE. I'm Alex McDonald. I'm an independent consultant and chair of the SNEAR Cloud Technologies Initiative. Before we go any further, I'd just like to remind you, you're able to get copies of the presentation slide by going to the Attachments tab. You'll find a link there that you can follow to pick the slides up. That's the first thing. And the second thing is, you can ask questions, should you wish to, during the presentation. And if we have the time available, and the question's relevant, obviously, then we'll answer it during the presentation. Otherwise, we'll answer it on our blog, the details of which I will give you at the end of the presentation. And last but not least, as you leave the presentation today, we'd really appreciate it if you could rate this on a scale of 1 to 5, where 1 is, gosh, what was I doing? I shouldn't have been here, all the way up to 5, which is great stuff. We'd like to see more. Just a brief overview of SNEAR. It's 180 industry-leading organizations that make up SNEAR, the Storage Networking Industry Association. We've got about 2,500 active contributing members and 50,000 IT end users and storage pros worldwide, of which you are some. You can follow us on snear.org/technical or on Twitter @SNEAR. What do the CSTI do? Well, we're more into cloud storage technologies. So we're in the business of educating, supporting and promoting, understanding requirements and collaborating with other industry associations all around cloud, not just storage, but cloud technologies, but with a particular emphasis on the storage element. Just a quick legal notice. We'd like you to honor the legal requirements of copyright. And the other thing is, if you use any part of this presentation and whatever you touch it with breaks into 2 parts, I'm afraid both of them are yours. There are no warranties with this presentation. Use it at your own risk. Notwithstanding that, we have some great experts today to take us through the topic of storage, HPC storage at Exascale. So we're going to talk about HPC's evolution and some real-world examples, the technology evolution of HPC storage, and HPC data storage and data mobility, which is obviously a big issue when we're talking about at huge scale. So without further ado, I'm going to let Torben take us away. Thank you, Torben.
Thank you very much. So I'd like to start with a quote from Rick Stephen at Argonne National Labs, that this is not your grandfather's HPC, and that most definitely pertains to storage as well. I've been in the business for more than 25 years, and more than half of that I've focused on HPC storage, which back in the day meant humongous disk drives in the 500 gigabyte range, all the way up to where we are today. And the change I've seen in the industry, the change I've seen in the customers over just the last 1 to 2 years, and more importantly, what I'm seeing changing in the next year, 2, 3 years going forward, is a major paradigm shift. And we still expect things to just move on nicely as it has for a long time, but that is no longer true. Back in the day, data was being generated. Now data is being ingested, analyzed, and new data is being generated in real time upon these things. We're not just talking about certain large files anymore, or pictures or what have you. We're talking about very different types of data, where some of those data are extremely small, some of those data are extremely large, and they're very often mixed together. we get into a situation where we're no longer talking about hundreds of thousands of files, we're talking about billions of files, many, many billions of files, and just finding a specific file, specifically if it's been named by an application and not a user, can be really difficult, and we need to speed that up because we can't wait forever. And that means we have new requirements on metadata in order not just to figure out how to staff them, read them, and so on and so forth, but also to find them and manage it over time. And on top of everything else, people keep adding new file formats to what we're doing, which makes things really, really complicated. And we also get into a point where just deleting a file is no longer easy because a file has many dependencies. You need to find them all, and you need to do it in the right order, and so on and so forth. And deleting files on a file system, specifically on a flash file system, takes time. It is not momentaneously. It has to take time, and you have to do trim and some other things. So that's putting an entirely new bias on how do you use storage, what are the components of that storage, and how do you tier that storage in a decent manner. And when you have all of these tiers put together, it becomes all about, as I've written at the bottom, location, location, location. Where is your data at any given time? Because it needs to be readily available to applications. And just to give you an idea about where some of these concepts are coming from, I take another slide from one of Rick Stevenson's colleagues, Pete Beckman, on a project called the Waggle project. Now, the Waggle project is one of the first real smart city initiatives, where the city of Chicago has more than 500 sensors spread out in the city and different places to measure not just the environment, but also traffic, movement patterns, fires, tremors, what have you, which means that the sensors in these locations are generating multitude of different types of data. That data is everything from radio waves to temperatures to LiDAR information to vibrations in the ground and so on and so forth. And the concept is that these sensors will not only be able to sense what's happening, they will also be able to report on it in real time, which means you need to do some machine learning of this. And that's another component in this equation that's really important. But in the back end, you have a supercomputer that collects this data from all of these different things, do the deep learning in real time, push data out again. And that means a significantly increased throughput of data going over the wire, not just locally, but in the cloud as well. And this is setting totally new requirements on how we build computers and how we build storage to support those computers. Another example is autonomic driving. As you probably heard, there's been some issues with self-driving cars over the last few years with deaths and some other things that's happened because the algorithms that is being used by the cars are not entirely foolproof yet. And those are usually in very normal weather patterns. I've been working with a few of these customers, and they're telling me that we can do dark, we can do light, we can do sunshine, we can do rain. Snow is difficult. Snow is very, very difficult because when it falls, it generates essentially a solid wall of information that the car can interpret and so on and so forth. So this requires the data analysis and the data ingest to be very, very large. And in some cases, we're talking about hundreds of petabytes. And that hundreds of petabytes is being serviced by a number of different compute platforms, whether it's just software, hardware, different types of models, and so on and so forth. A lot of this is simulation, but it's about doing simulation, testing that simulation in real life, getting the data back in again, and so on and so forth. And you have a continuous loop of information, everything from the cars on the left that ingest the data to the actual output that goes back into the cars and so on and so forth. And that process is, first of all, requiring some massive amounts of data because we're talking about video data, picture data, LiDAR data, sensor data from other things. And just to give you an idea about some of the throughputs we're talking about, This is from a real-life case in Europe that we've been working with a customer that is currently in the first phase of this. And the first phase essentially requires the test vehicles to upload once or twice a week. And that essentially equals to about 1 petabytes of data per day being ingested in systems. Now, this has been done in the cloud on the edge, which requires fairly decent throughputs to the system, and so on and so forth. But there are some bottlenecks, and you get, a need to be able to do this. Now, from the ingestion, it goes into a massive single namespace, about 185 petabytes at the moment, but most likely to grow to many times above that. And then you can see some of the numbers, like the system in the loop, so software in the loop generates about 700 or almost 500 gigabytes per second throughput into the system. The back end of this is all about doing 200 gigabytes per second into an archive, because you need to be able to archive all of the data you have and all the results you have for a legal purpose in the future, and so on and so forth. So inside this data center, you essentially have performances exceeding 700 gigabytes per second, on a 24/7 basis, 365. Now, it's not that hard at achieving that, but it is hard achieving it over time, where you have to do it day by day, month by month, year by year, and continuing to grow that data and continuing to support the hardware that has to do all these things. So a lot of challenges. Now, there are some things helping us here to get better performance. We are moving from a PCI Gen 4 to PCI Gen 5 very soon, which allows us to do much quicker IOs in the systems and so on and forth. Our core networks for computation is moving to 400 gigabits per second. Now, you can always discuss, do we really need 400 gigabits per second? Well, we discussed that when we had 200 gigabits per second in the last generation. And guess what? Storage can gobble that up in no time and utilize that easily enough. So yes, we need more performance. We now also have some new strains in systems where the GPUs sitting in the autonomic learning systems have ways of bypassing the CPU. That means they can ingest, use data at much, much higher rates than earlier. And these systems just get better and better, larger and larger. And that means we need to be able to support a number of these things at the same time, which also puts, again, strain on the hardware. And finally, we are getting to a point where we now have workload managers interact with the storage, not just the compute, but with the storage, to make sure that it can reserve enough performance, that it can reserve the right data at the right place. We're back to location, 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 and so on and so forth. And these things, again, make sure it requires the storage to be a very solid component of the entire solution. And all of these technologies will enable things, but they will also create problems for us who design these systems. So to give you a little bit of an overview, if we look at a traditional system, and this could be a cloud-based system, or it could be an on-prem system, or a combination thereof. We have our compute system on the left. It's usually based around standard CPUs or a combination of CPUs and GPUs. Now we have the ability to add persistent memory to some of these nodes. Now, persistent memory means that the latency to that storage that still survives the power of is almost the same performance as we have with the RAM memory of a computer, but we can do a little bit more of this. Now we can take that memory and we can add a file system onto that, like DAOS. That means you have a distributed file system running in the compute memory system rather than on the side of things, which gives us much higher IOPS, which gives much higher throughput and allows us to do things we couldn't do in the past. Now we can also add NVMe drives to a lot of these nodes, which is also fairly common. In the old days, in some cases, they're used mostly for local scratch, but there are coming new technologies that allows us to use them a little bit more intelligently. We have the compute system as the storage system that we've always had, which is either Lustre-based or Spectrum scale-based, or even now systems based on NVMe or Fabric. Regardless of what file system we're running or what type of system it is, they are usually a combination of NVMe drives and spinning drives because of cost, especially if you need large capacities. Now that generates a new challenge of data placement and data movement within the storage system so that we can utilize the performance of flash, but also manage data on disks in order to have a good price performance of everything. And in between these, now we have the fastest possible networks. As I said, at the moment, there are 200 gigabit networks, whether they are Ethernet based or InfiniBand based, doesn't really matter. Performance is the same. But it also allows us to do some other new things. So, for instance, in Lustre or Spectrumscale, we now have things like persistent client cache, or LROC as the equivalent is called in Spectrumscale. Now, this allows us to do things on the compute side that still interacts with the file system, but doesn't have to move every single bit over the network, but only the pertinent bits, which again allows us to do computations at a order of magnitude faster if it's very storage intensive or data intensive. But this is not enough. We need more. We need a backend that allows us to store a humongous amount of data for long periods of time. Some industries, like for instance the airline industry, Airbus and Boeing and so on, they have to save every piece of scrap data for an airplane, every single airplane, for 50 years from the time it's being built to after it's commissioned, in order to be able to follow the data path. That means exabytes of backend storage. Now that can be very slow storage like tape or in cloud, but it needs to be there, and we need to interact with the front ends when need be. Now that means that again we need fast network to the backend, and we need a mechanism for moving data between all of these tiers. So the view of the future in my mind is we need a way to create a single virtual namespace that ranges from the memory of the supercomputer all the way back to the tape storage in the other end. And that is essentially our single virtual namespace. That means that's where all the data is. That's where we'll find all the data. That is where the data lives for the entirety of its life. Now, as I said, some of these requires essentially remote data memory access in order to work fine. That also requires non-blocking networks, which we do have today. But it also requires us to do more flexible I/O. We can't just have one size fits all. That's why I've added things like the persistent client cache or LROC to this. Why NVMe or Fabric can create targets for very fast solutions where you need a dedicated namespace for a limited amount of time, and also needs persistent memory. Now, it also does mean it puts some extra onus on the applications. We need new types of framework for some of these extremely high bandwidth situations, like the PGAS type solution that can do non-POSIX I/O. That means we don't have to adhere to some of the old, very cumbersome rules of how to place data and how to name data. We can do it much faster. We have solutions like DAOS that doesn't even run in standard storage. It runs on persistent memory, which is interesting. We have file systems such as Cortex out of Seagate that allows us to do something totally new with data resiliency over time and so on and forth. And some new interesting file systems such as DeltaFS that essentially does checkpoints at every single step of the way. So it doesn't save data, it doesn't change data, it creates a snapshot every time data changes. Now, we also have some requirements on data service about being able to move between NVMe's and disk drives, and this has to be done in such a way that it's very transparent, but it's also very fast, and it has to be intelligent. Now, there's a lot of things going into this that we don't have time to go into detail on this presentations, but this is an area where we put a lot of effort in at the moment, a lot of research. Same thing with the search facility. It needs to be unobtrusive. It doesn't allow you to monopolize your storage to find data. It has to go really fast, and it has to have low impact. And again, this is something that is also been a lot of focus and research, both at our company and in the industry as a whole, as well as a lot of academic sites. So a lot of things are changing, and we need to be able to put all of these things together. Now, the data management, which is the back end of the equation, has the same challenge. And we're also seeing a lot of new concepts and ideas coming into this picture. And again, we don't have time to go into every single point in detail, but you get an idea about some of these details here. And that essentially is the end of my slides, and I now hand over to Alex McDonald again.
Thank you, Torben. That was really good. Thank you. I did have one question, actually, about file systems, which are my particular hobby horse. You were talking about non-POSIX file systems. Does that mean applications need to take HPC considerations into account? Can we assume that we're going to have to change the way we write applications or application interfaces to get access to these new file systems?
Yes, essentially it does mean exactly that you need to be more stringent about how you store your data. Now, you can always trust the file system underneath, or if it's raw data, to handle it in a secure manner. But the way you access the data, the way you secure that data from a traditional locking point of view, which application can do what and so on, that requires a lot more work on the developer's point of view. But the gain is so humongous. I mean, we're talking about 10 order of magnitude faster IO on these systems, that it may be worth it. But we're not quite there yet because the tools aren't there.
Thank you. I do like that word, humongous. It's a great word. Now we're going to pass over to the technology evolution of HPC storage with Michael Henneke. Michael, take it away.
Thanks, Alex. So yeah, after Torben has emphasized the changing workloads in and beyond the HPC storage, I'll take a little look at the technology perspective, both from the hardware and the software side, and focusing a little bit on the classical HPC space. So first of all, maybe to distinguish HPC storage from the non-HPC storage, like what's happening typically in cloud infrastructures. In HPC, the typical scenario is that you have a large number of client compute nodes that are connected to the storage through an HPC fabric, nowadays typically something like InfiniBand or high-speed Ethernet. And then in order to achieve your capacity and performance goals, of course, you have to scale out a large number of typically identical or very similar building blocks. And in the traditional storage solutions, those are hardware redundant systems like pairs of servers connected to a storage system with hardware controllers that have connectivity to all the disks, very much like in traditional environments, right? The difference between, let's say, a typical traditional cloud deployment in the hyperscale world and HPC is that in the HPC world, you will have many cases where all of the compute nodes are working on the same problem, rather than every compute node has their own type of workload. And they all access this shared storage as a global resource, rather than just like provisioning one VM per client, and then they are pretty much independent. So there's a much, much higher degree of coordination that is required in the HPC world. And just as we have seen in the traditional storage space, there is a strong move away from hardware redundant building blocks with dedicated storage hardware to like software-defined storage systems. But again, there are different requirements there in terms of concurrency, and there's different requirements in terms of performance. So while the base technology is very similar, the actual sizing of those systems is different. In terms of managing the concurrency, there are really two dominant parallel file systems out there that Torben also mentioned: Spectrumscale, which is a closed source parallel file system mainly developed by IBM, and Lustre, that has been driven through the open source community in a lot of the national labs. So those are like present in a lot of the large supercomputers, and well beyond that, expanding into the other workloads that Torben had mentioned. Now, there over the years, I mean, those systems have evolved, and the story we are seeing again and again is the tiering story, right? In order to keep up with the evolution on the storage side, we really have to combine different storage technologies now. Typically, the obvious thing is SSDs and HDDs. And we've also seen in Torben's slide that there is a lot of local storage in those systems right now. I would claim that in many cases, those local storage solutions are really meant to plug holes and deficiencies that we're seeing in those global parallel file systems. And the solution, or the attempted solution, is to just like move some of the I/O to the compute nodes locally. You don't really want to do that. You're forced to do that because of limitations we're seeing on the global scale. So I have one slide for Lustre and one slide for spectrum scale, just to show the technology evolution. This is from a 20 years anniversary Lustre presentation 2 or 3 years ago, where they started in 2002, going up to 2020. And you're seeing, like in red, you see the capacity increase. In greenish, you see the performance increase. And the y-axis is logarithmic, right? So this is really exponential growth. At the bottom, you also see the disk capacities going from like 100 megabyte to 16 gigabytes nowadays, and the fabric evolution on top of that, going from a 200 megabyte per second Quadrix network in 2002 up to like today's InfiniBand HDR, which is 20 gigabyte per second, right? So orders of magnitudes in both capacity and performance. Now, the performance of the individual disks didn't change much over those 20 years. So how did we get exponential growth on the performance? 2 answers, right? More parts, like going from 1,000 drives to 10,000 drives gives you an order of magnitude. And of course, SSDs entering the picture also gave a performance boost. Those 2 in combination allowed us to grow the performance exponentially. Now, if we look at the functional picture here, I just picked a GPFS evolution side, which has been around a little longer. And in purple here, I'm circling some of the large HPC systems, in particular the ASCII white, ASCII purple systems, which are roughly like 10,000 drive systems in the early 2000s. Those were very early, very large HPC storage systems. In the deployment of those, a few painful lessons had been learned in terms of reliability of those systems. So one thing that also needed to develop to scale this like orders of magnitudes bigger was better ways to protect your data with redundancy, so going from 2 parity to 3 parity codes, and also being able to manage large parallel systems in a unity. Like if you build storage systems out of, let's say, 50 individual block storage controllers, and you run a parallel file system among them, even figuring out which of those 50 systems has a performance problem is extremely hard, because in a parallel application, all of your storage systems will slow down. The slowest member will dictate the performance. So a lot of storage management infrastructure has been developed. And in yellow here, I'm highlighting on this product's history, right? There was a lot of focus on decluster rate and moving some of the management functionality away from the storage hardware into the software layer, just to manage those orders of magnitudes, a larger number of parts. And that has been in place in many other storage systems also over time, of course. So let's now take a peek at the what we call the top 500 list, which comes out twice a year, and it ranks the largest supercomputers in the world essentially by their computational performance. So how fast can they do a floating point matrix multiply, essentially. I just grabbed the top 5 here for illustration. So this is a mix of systems in Japan and the US, in China. There's also a European system on the list a little further down, and just show you the order of magnitude we're talking about. The number 1 system right now is 158,000 nodes, over 400 racks. The newest entry in this list here is the one at the bottom. Of course, performance is increasing exponentially, so which with like much less number of racks and number of nodes, they're getting also pretty high on the list here. Important for those systems here is also the view on the file system side. So the number 1 is the Fujitsu system that is actually based on Lustre, and it does have internal SSDs in the system. Roughly like 1 out of 16 nodes has a local SSD. Then the other next two systems are running spectrum scale. Again, both of those systems use the global parallel file system, and then they have no local NVMe in them. We don't really know what is in the Chinese system. And then on the number 5 on the list here, this is actually a pretty large, pretty ambitious 35 petabyte all-flash Lustre system that was set up at NERSC. They have, of course, their data center disk systems for larger capacity and long-term storage, just like Torben mentioned in his slides. So that's the top of the list today. When the Lustre history slide was done, the stuff on the top right wasn't actually released yet. Those are those two systems that are coming online very soon here now in the US. On the left-hand side, I'm showing this example as a traditional storage system. This is an AMD plus GPU-based system with over 1.5 ExaFLOPS. This is the traditional storage design with a Lustre file system, 47,000 disk drives, a flash tier, and then also in-system storage with local SSDs in the system. Whereas on the right-hand side, this is like Intel CPUs plus GPUs, many GPUs in those recent systems. This is actually going a completely different direction. The primary storage on this system is a single DAOS all-flash system with NVMe and PMDK, which is targeted to achieve over 25 terabyte per second, and it's 230 petabyte of capacity. So in this case, no internal drives. Of course, also in that center, there's other storage around that, but the primary storage really is just a single tier. So those are coming live very, very soon. Now, let's look at the DAOS system. And I'm a little biased because I'm in the DAOS engineering team here, but I wanted to highlight what the main features in DAOS are. DAOS is managing storage through essentially two open source frameworks, PMDK to manage a persistent memory or storage class memory, which handles all the metadata and very small transactions, smaller than 4 kilobytes, and SPDK to manage SSDs. There's no support for Linux block storage, like no spinning disks, no traditional SAS SSDs. And then on top of this DAOS storage engine that's built on PMDK and SPDK, you have your application frameworks. And Alex had a question about, like, do you have to change your applications? Yes, I mean, some of the key users will change the applications, but for the general public, if you will, right, you will depend on frameworks in specific areas that get adapted to those node storage systems. So we don't expect everybody to program directly against something like DAOS, but rather use Spark or MPIIO or PyTorch or some of those frameworks here. And this technology gives you a lot of advancements in also what can be done in software. The key ingredient here is really the persistent memory development kit, which has been covered at SNIA extensively, right? What this does essentially is it allows byte level access to persistent memory. And there are a number of libraries in this PMDK development kit that are meant for different purposes. For DAOS, mainly we're using the PMDK object, which gives us a transactional interface to objects, right? So we can replace the locking that is present in traditional parallel file systems with a transaction model where we can be opportunistic. We can just like commit writes to the file system, for example. And if normally in an HPC application, everything is well, there are no collisions. So eventually you wouldn't have needed your locks, but you have to do them anyway because you have to safeguard the data, right? If you have the ability to be transactionally safe on a persistent memory layer across a large cluster with distributed transactions, now you can just protect your IO operations with those transactional semantics, right? And all the applications can just do their writes. And if a collision happens somewhere, rather than having slowed down everything by locking, when you just roll back the last transaction that produced the collision and do it again, right? So the approach of ensuring consistency is very different and allows us to optimize for performance in a way that wasn't possible without persistent memory and without this transactional capability. So it's not only about the hardware speeds and feeds, it's also about the programming models that we can use to implement those new storage systems. And the way this is utilized within like a traditional environment is that your NVDIM or SCM modules are controlled through a Linux file system that is persistent memory aware. You're essentially when you're mounting that file system, you cut out the Linux page cache. You don't need a page cache. You need to move from virtual memory to the DIM because you can directly byte address the NVDIM. And then as soon as you have mounted that, then the application can memory map that range of memory directly into the application, and you can read and write at byte granularity to your persistent memory. So that's a very elegant way to access persistent memory, not through a block level interface, except for the initial mount, right? But really through loads and stores, and get transaction consistency on the application level across a large number of nodes, not only on a local node. So PMDK is really key to develop those new frameworks. And then if you look at this from a more an application view, there's DAOS stands for Distributed Autonomous Object Store. It's not an object store like an S3 object store because of several differences. One is we can actually modify the objects, right? It's not just a put and get. If you want to change something, you have to get the whole thing, modify it, and then put it back into the object store. You can do in-place modifications, and since we have this transactional consistency, we can do that very efficiently. And then, of course, it's on very high performance storage. We can do versioning. We can support different abstractions. And a POSIX file system layer is just one abstraction. We can model HDF5 containers. You can model key value stores, which are persistent. So you can directly like work in Python with a Python dictionary, which typically lives in DRAM memory, right? So every time you close your application, you have to flush it out to disk somehow and read it back when you restart the application. With those types of interfaces, you can essentially bind your Python key value store or dictionary structure to a container that is formatted for this on persistent memory plus NVMe for the bulk storage, right? And the data stays persistent. You don't have to read and write. You just open and link to this key value store, and you're ready to go for the application. So very promising. But again, it needs some changes on the code level, right? Either in a framework or in the actual application, if that's worth it. So going forward, there are a few other technology developments that we're really watching because they open up new opportunities. In this big picture of different storage hierarchies that we've seen several times in the presentation here, there's always this notion that you have physical boundaries, right? You have to distinguish between stuff that is in the compute nodes versus stuff that is in the storage nodes. And there's a lot of data movement complexity involved with that. And of course, there's performance implications depending on the fabrics that you're using to move data between, let's say, the compute and the storage side. One thing that may allow us to make those transitions a little more fluent is actually the CLX standard that is getting ready for its 2.0 version. And with 2.0, we're getting the CXL.mem mode that allows us to use CXL not only for storage and other like fabric adapters, but also for memory attachment. And one area that we are really interested in right now is to use CXL going forward to provide something like a rack level fast storage where we don't need to put local SSDs into the compute nodes, but rather have a more centralized, shareable storage device within a rack, and then you use CXL, including the CXL.mem interface with like load store semantics just for memory, to disaggregate those local SSDs from the compute nodes again into something that is very efficiently connected on a rack level. And then, of course, going out to the central storage, you would still need something like an InfiniBand fabric or like 100, 200 gigabit Ethernet fabric. Because honestly, if you look at all of those systems with local SSDs, there is no standard on how to use those SSDs. Very often the users are responsible for manually copying data back and forth between the different tiers. Every one of those large sites that I showed has their own implementation of software to run on those local SSDs. And for the end users, it's really painful. It has been born out of the necessity because, for example, metadata operations on a large parallel file system sometimes really bring the system to its knees. So in order to isolate stuff, it was good to have another storage system. So you're running those workloads essentially on local scratch. But with CXL now, we can change the boundaries a little bit. So we don't need to populate in compute nodes. We have something that is more easily manageable. Hopefully, we can also run like more global namespace type storage software stacks on top of that. So this will hopefully allow us to get a little more flexible with the storage deployments. One thing also to note is that initially when people put local SSDs into a compute node, that SSD provided a pretty good performance boost. But now with the networks becoming so fast, it is quite typical that a remote NVMe is actually faster because you can rely on a 200 or 400 gigabit network than just putting 1 or 2 SSDs locally into the compute node. And again, here, if we get a new fast interconnect with the right semantics and the ability to do load stores, then yeah, we can design the data center for those huge systems a little different. So we're expecting to see more rack level integrated stuff in addition to the traditional model. All right, with that, I'm done with my part here. So Alex, back to you.
Thank you, Michael. Just a quick observation. We have a number of persistent memory presentations, and in fact, there's a whole persistent memory part to the website at SNEA. We'll add that to the blog that we do, and we'll point links out to the persistent memory pieces and also to the CXL pieces that we have from our SDC conference. They're also available. I'll make sure that when we do the blog, all the relevant pointers are there for people to pick up extra information. Thank you very much, Michael. It's very helpful. Now I'm going to pass over to Glenn, who's going to talk about HPC data storage and data mobility. Glenn.
Thanks, Alex. And thank you to Michael and Torben for making my life so difficult now, having to follow not just great speakers, but also really interesting topics and a compelling view of exascale storage. So thank you for that. So actually, I'm not going to compete so much by talking about storage. I'm really going to be talking about data and the impact of looking at exascale type workloads and what we need to do from a data mobility perspective and data management perspective. So first of all, let's just look at how data exists in the current HPC storage ecosystem. And this shouldn't be a surprise to anybody, hopefully. Firstly, there's the operating environment. So that's the operating system that we're actually running from. So the binaries that are in your kernels, all those sorts of things. Obviously, that's a per node type install. Then you have scratch space. So scratch space is really what the system uses when it's doing high performance calculations. I just needs an area to write things out to as a intermediary before it gets onto the next calculation. So it could be when you're doing sort of back in the day when you were doing MapReduce, it would be where you'd have the swaps written out to. But it's essentially there to extend memory. Now, as we're seeing from the exascale systems and all the things that Torben and Michael have been talking around, that's becoming less and less of a problem. But it was traditionally, that was something that needed to exist. Then we move on to the data itself that you're going to be using for the computation. Now, as we move towards exascale, obviously the amount of data that we're going to be processing becomes huge. They're extremely large data sets, but they're fundamental to the jobs. And the whole idea of having the exascale environments is so we can get so much more of that into memory to be looked at simultaneously rather than having to sort of page across it, build aggregates and come back and do several passes at it. However, we're still sometimes looking at subsets of a very much larger data set as well. And we'll have a look at some examples when I move forward in a minute. But also, we're looking at combining multiple data sets. So you're aggregating, you're bringing together different features from different data sets as well as you're building new use cases, and we'll see why. And then finally, obviously, we have our users' home directory, the less entertaining bits, but that's where their code sits. That's where the binary sit. If they're building AI ML models, for example, that will be where their notebook and their source code and everything like that sits. And very often, you'll see users that aren't necessarily trained on certain HPC systems trying to run jobs in their home directories as well. So you have to take a little bit of care of where they get placed. So that's what traditionally it looked like. Now let's look at the mobility requirements here. So in an HPC system where imagine this is an exascale system, so my blue dots represent that. We've got our simulation that's going on within that. So that's the memory space, the disk space we have within the cluster simulation. So how do we simulate? Well, firstly, we're going to need, we have the home directories where the binaries are. That's where the executables are coming out. And we have our computation data. So that's from the pillars we saw on the previous slide. All of this is pretty self-contained, and when you have build a silo for your HPC system, this is pretty much what it looks like. However, these days, particularly with the kind of exascale and moving into sort of the convergence of AI and ML and HPC as well, we're beginning to see that ecosystem expand beyond just these walls. So we have applications. The more we can do on the HPC side, the more in real time we can do, the more we're going to have to be able to surface that to people who need to know. And so if we're doing sort of real-time predictions of weather patterns, those sorts of things, we need that application, we need that visual interface so that whoever's defining what the outcome is of that data is gets a view as to what's going on. Now, it might not be a visualization interface. You might be doing something like plugging it into an automation system, so you take actions based on what's coming out of that simulation. So where does that computation data come from? It doesn't just sit there. It's not born in that that ecosystem. It doesn't just kind of live there forever. So very often it's getting pulled from an archive. Now, you're probably not pulling everything from the archive because the archive is going to be massive. If you look at just a small example of satellite imagery, for example, the resolution and the size of the images we pull down from various satellite constellations are huge. And then when you do processing against them, you create new data sets and new data products against them that increase the size again. And so pulling all of that into something that's going to look at those images and make some kind of call around, again, weather patterns or erosion, all that kind of thing, it's very difficult. You're not going to need all of the archives. You'll select certain patterns. So there's filtering that happens to create that computational data store. Now, when you're doing that, you generally need to apply some business data to it as well. Now, I've called it business data, but basically this is the data that provides context to what you're pulling out of the archive. So it might be something that's coming from more structured data sets, such as databases, that allow you to build those filters to know exactly what you're pulling from an archive data. That could be a SQL query that gives you a certain list of genomes that you need to look like if you're doing genomic research and you're pulling sequences from the archive that have been done previously against DNA, that kind of thing. But it's the pieces that add the context to the filter so that you can automatically pull the right data from the archive. Now, as we heard Torben talk about with, I think it was the Waggle project at the beginning, Edge is featuring more and more in this. So we have a bunch of data sources that live out at the edge. Now, this could be video, it could be telemetry, it could be personal devices. All of these things are creating data that will then get fed into a system, which could end up in the archive and then into the computational data itself. Others are being processed live. So you'll see more and more compute that moves out to the edge as we're starting to do inference and even training from an AI and ML perspective at the edge, but also computationally speaking. So, and if you imagine that edge data source as being that constellation of satellites, even, they're a streaming data source that are pulling data in from strange areas, in this case space, and pushing them back into the HPC cluster to do things. Now, there is a real clamor to be able to get processing against that data as soon as it comes down, particularly if you're doing something like weather pattern control, or you're looking at earthquake risk or anything like that. So how do you get that data into the cluster where you can do that simulation as quickly as possible? Well, there's two answers to that. The first one is have the emitting point as close to that cluster as possible. So you're setting the clusters up at the base station where that data is coming down. The other piece is you're moving the compute to the edge. So you're doing some of that compute and some of that filtering and some of that pre-processing, if you like, on the edge piece itself. So possibly on the satellite or a space station or whatever it may be that's producing the data. So you're moving the compute out. So you have two options, move the compute out or bring the data in. So this is just a kind of a view of basically an enterprise data platform functional architecture. So this is what we're seeing in businesses today, and this is not necessarily related to high performance compute, but what we're seeing is the convergence of these sorts of architectures with what we're seeing in the HPC environment as data spills beyond the boundaries of something we can control. So enterprise have been doing this for a long time. Enterprise have always been limited by the storage platforms and persistence platforms that they have from a capacity perspective, and often from an IOPS perspective as well. So they're good at solving the problem of how do I get beyond my physical capabilities in terms of being able to index the data, use metadata to let me know where it came from and let me know what sort of data it is and how to address the data, through to bringing it into hot storage online and then doing some processing and analytics against it. So we can learn a lot from the way enterprise is doing this. Not to mention, enterprise is also very good at things like the governance and security and trust of that data. HPC clusters tend to operate in what's traditionally a very secure and isolated environment, should we say. So they're built in silos. Now, they do have lots of tenants, so they have lots of sort of academia and researchers and things working on the systems, but usually they all have access to the same data sets and the same kinds of data, even if they're working on different parts of it. So governance and security and trust hasn't been at the forefront within an HPC environment. If anything, it might be something that slows it down and impedes it in some way. But in enterprise, it's critical, and you need that whole end-to-end audit trail. Now, as we start moving into HPC that is working on alongside many organizations. And when we get to Exascale, one of the benefits is you can have lots of organizations collaborate. There's going to be a need to wrap more governance around the data that we see there, and security and trust around the data, so that we can securely share. Now, as I gave that example around the satellite imagery, how do we make sure that the right parties get access to that data when it comes down immediately, so that they can perform the research they need to do against it, without necessarily having somebody that's doing I don't want to say a hobbyist project at Exascale, it's a bit expensive, right? But something that's not as critical, but taking the processing power to do that. So governance can help us with that sort of thing as well. And then obviously there's the sharing piece, but also the end-to-end lineage of that data. So where did it come from? What's happened to it? What am I doing with it now in the Exascale system? And then what am I getting at the end of it? So that lineage becomes important, particularly in things like medical research, where you're building drug profiles and that kind of thing, to know why you've come to the conclusions you've come to and be able to back that up with data. And then obviously on the infrastructure level, you have your standard building blocks, if you like. From an ingestion and distribution piece, we now need to start thinking, as I said in the previous slide, around non-real-time and real-time flow. So how do I bring things directly into the system to process? From a storage process layer, we see all of the usual suspects. Object storage is obviously making a large impact in the enterprise. It's always been there. So Lustre itself is an object storage, even if it's not addressed that way necessarily in some of the file systems, but it's built around an object storage and metadata layer. But we're beginning to see all of these things sort of converge in that central layer now. And then we've got our usual processing and analytics. We can't forget about our traditional analytics piece and our traditional sort of BI type platforms. They're still there, and they're still adding value to all of the things that we're doing. But typically, this is where you'll see the simulations and things. And then I mentioned data access and visualization previously as well, in the value that has in terms of real time. And so it's not just about sort of being able to visualize the results in real time. It's being able to search on the data sets to be able to identify what it is you're actually going to be pushing into the simulation in the first place, and seeing the lineage that you're building with that data as you're going through various engineering phases, doing data transformation, ETL, that kind of thing. And then obviously from the governance perspective, you're managing not just the infrastructure and the governance around that. So we're not looking at access at an array level anymore, but at a data object layer. And then finally, this is an example of the two worlds colliding, essentially. So on the left-hand side, in that kind of deep blue, you have a streaming data processing pipeline. And on the right-hand side, more of a batch processing, so what you typically see in an HPC environment traditionally. And we're seeing those two worlds collide. So these sorts of applications are going to have to exist side by side and allow access to different aspects of the data. What you don't want to be doing is moving the data around to different systems to do each of these sorts of activities against them. So the data will be going into that central pool, that highly accelerated and memory-driven pool, and then we'll bring the compute to the data in this sense, where we have things like Spark, where we can do those real-time analytics against it and streaming processing, and then we've got the MPP stuff going on the other side. So in summary, then, we're moving very much towards a convergence of traditional AI and HPC workloads. HPC can learn from enterprise, though. Enterprise has solved some of the problems that HPC is now seeing in terms of growing beyond its own borders. And so there are things there that can be learned. Ingest of data has always been a problem. But now with the sheer scale of that data, it could literally be a blocker to what we're trying to achieve. And then finally, Exascale is going to require both data and compute mobility. We have to move data to the compute and compute to the data as the jobs begin to span not just our data centers and clouds, but also out to the edge as well. Back to you, Alex.
Thank you. Thank you, Glenn. We've got a little time. I'm going to ask the same question to all three of you, because I'm probably much like your average Joe when it comes to big numbers. I mean, we've had some extraordinarily big numbers. I mean, they've got more zeros on them than they really decently ought to have. And my question for you, is HPC a rich man's game? I mean, the scale appears to have increased dramatically over the last few years. I mean, we're talking about exponential growth. We're making it look like straight lines, but they're actually logarithmic. And the is the IT cost increasing to the point where this has become simply a rich man's game, or has the cost decreased to the point where small to medium-sized enterprises might be able to indulge in doing HPC type activities? I'm going to start with Torben.
Well, I would say both. I mean, to build these really super big systems, you need hundreds of millions of dollars to do so, because the sheer cost of infrastructure just goes beyond anything that we've seen in the past. But on the other hand, you also see an HPC system in the most unlikely places. I mean, we recently sold an HPC system to Zalando, which is a retailer, web retailer for mainly shoes, but other things. And they have a Lustre system now, drives their backend. And that was a fairly decent system. It outcompeted a standard NFS solution for these guys. So we see every state going in different directions. Price has definitely gone down significantly on these costs. I mean, essentially, the cost of a large storage system now is the same as it was 10 years ago. It's just that now it's 100 times faster and 50 times larger. So that there's a definitely decrease in cost, but it's not cheap to do any of these things. It's because of the amount of hardware you need. But
okay, Michael, are you seeing the same thing?
Yeah, I mean, we like to say that these types of HPC systems are more like a time machine that show you what will show up in the general enterprise world a few years after, right? And the cloud space is a prime example, right? All of the large HPC parallel file systems are now being adopted in the cloud, right? So we get a combination of the deployment mechanisms coming from the cloud world with the scale and robustness of the storage software infrastructure, right? And those are married together in very efficient ways. So yeah, I mean, not everybody will build like a 200 petabyte all flash system for those types of use cases, right? But the same technologies and the same software layers can be used at all scales, right? I really believe that this is like the research lab for what will become mainstream pretty quickly, like often faster than we thought. And then on the cost side, another aspect that we haven't covered here is also this old notion of like tape is dead, disk is dead, and always the next technology is replacing the old ones, right? That hasn't happened, but certainly as new technologies arrive and cost structures change, you also get shifts in like dollars per terabyte or dollars per terabyte per second, which is more the HPC metric, right? So how do we get in QLC drives to lower the price of flash and then build larger systems out of that, right? That's also technology explorations that are done at this level here and then benefit everybody.
Okay, that's interesting. I particularly like the idea that we're inserting wedges of faster stuff closer to the processors, or we're moving the processors closer to the faster stuff. But the old technologies that we've always depended on, like tape and disk, and even now flash, just shift left slightly, and the cost profile changes. Glenn.
Yeah, so being the consultant of the group, I guess I should say it depends. And it depends on how you want to define HPC, right? So I've got a device on my desk in front of me at the moment that I can fit in the palm of my hand and has more than 1,000 graphics GPU cores in it. And so that costs under $100. So I can build a cluster of 10 of those for under $1,000. And you go back 5 years, that would absolutely be classed as HPC. Just the amount of cores and the amount of processing I can do on it. So these things are shrinking and becoming far more affordable and far more commodity at the low end, meaning that we can put what was traditionally sort of an HPC cluster and run it on things like Raspberry Pis at the edge somewhere. So you can absolutely get the architecture and what was previously seen as that kind of parallel batch processing against many cores for next to nothing. As Michael said, it's really the time machine, and this is we're catching up with what was HPC back when I was sort of looking at HPC originally. But as Torben said, the big stuff is always going to cost the bucks. But I think it's affordable to get something that you can play on and work as an HPC system. Absolutely.
Okay, good. I'm always pleased to hear that. Expect one in the data center near you shortly. I suspect might be the message. Gentlemen, thank you very much. Thank you, Torben. Thank you, Michael. Thank you, Glenn. And thank you to the audience for listening to this webcast. A reminder, rate this presentation on the way out and provide us with some feedback. We're always looking for indications as to whether we're doing the right things and whether we're doing the right things well. A copy of the webcast and the slides, you're going to be able to find that in the SNIA Educational Library. And we'll post up a Q&A, including some of the pointers to some of the persistent memory pieces, HPC pieces, the CXL piece that have been talked about today on that blog. And you can also follow us on Twitter at SNIA Cloud. In the meanwhile, thank you very much. Have a good rest of your day, whatever that might consist of. And thank you very much to our speakers today. Take care, everyone.
Thanks.